Hello everyone, I am Dr. Sudhan Sharma from School of Computer and Information Sciences in Indira Gandhi National Open University, and today we are going to discuss about mathematical induction. This is a very interesting topic because it is generally used to prove the theorems. So far as this session concerned, the objectives are to understand the principle of mathematical induction and apply the principle of mathematical induction to establish the truth of several formula and inequalities for each natural number. Now, in order to formally understand what is mathematical induction, it is actually a proof technique wherein we apply the mathematical concepts which are quite simple to prove the statements about some positive integers or the natural numbers, and it is especially useful for proving the propositions. Propositions and predicates are actually the statements which are either true or false, and these can be applicable to infinite sequence or in cases and to many formulas and inequalities. Actually, this principle of mathematical induction works because it creates a domino effect. That is, by proving the base case and showing that each case leads to the next, you are able to ensure that all subsequent cases are true. In order to understand it in a better manner, say we are having a sequence of books lying in a sequence. Likewise, if we drop one book, then all cluster of books will fall altogether. That means if a situation is true for an instance and it is true for nth instance, then it should be true for the n plus 1th instance also. Now, in order to understand it in a better manner, let's begin with an example to say we want to understand that what is the sum of the first n odd natural numbers. Now, 1 is also an odd natural number, so sum of 1 will be equal to 1 only because 1 is the only sum n. But the second natural number, second odd number is 3. So, 1 plus 3 will be equal to 4, and 4 will be nothing but 2 square. But that means we are taking two odd natural numbers. Now, if we take the third odd number into the consideration, that is 5, then 1 plus 3 plus 5, that turns out to be 9, and 9 is actually the square of 3. So, on the same line of action, if we want to understand the pattern, then we can understand that 1 plus 2, 1 plus 3 plus 5 is 3 square because 3 terms are there. 1 plus 3 plus 5 plus 7 is 16, that is 4 square, and we are having the 4 terms. So, that means the pattern followed is that if there are n terms, then the total sum will be equal to n square, where n is the number of odd natural numbers. Now, jumping into the conclusion by judging from the pattern formed by the first say 10 sums, we may find that it is 10 square. But to the conclusion that it will be true for n terms, then the sum will turns out to be a sequence like 1 plus 2 plus 5, 1 plus 3 plus 5 up to 2n minus 1. Now, 2n minus 1 will be odd number. So, nth odd number will be 2n minus 1. So, the sum up to the nth odd number will turns out to be n square. Now, simply jumping into the conclusion is generally not logically valid many times because it is observed that sometimes the pattern is very successfully running up to say nth term, then at some other n plus 2th, n plus 3th or n plus some mth term, the pattern is not followed. So, the question arises that how to legalize a pattern. Then one way to legalize a pattern is to follow the principle of mathematical induction. So, let us return to our question and try to understand it with the method of principle of induction, that what should be the sum of n numbers, and is the pattern that sum of n numbers is equal to n square is valid for any number. Now, the sum of n numbers, n where n is an odd natural number, then 1 plus 3 plus 5 up to 2n minus 1 turns out to be n square. So, now if we are going to have the next odd number, then the next odd number after 2n minus 1 will be 2n plus 1. So, that means the sum of n plus 1th odd number will be equal to sum of n odd numbers plus 2n plus 1. We are observing over here that Sn is equal to 1 plus 3 plus 5 up to 2n minus 1 will be equal to n square. Now, to have the better understanding, the 2n minus 1 is an odd number. So, 2n is an even number. Now, 2n plus 1 will be the next odd number. So, in order to have the sum of the next odd number, we should have the sum of n plus 1 term will be equal to sum of n terms plus 2n plus 1, which is the next odd number. Now, if we follow the pattern, that if we say that Sn is equal to n square is a correct pattern, then we can rewrite this equation Sn plus 1 is equal to Sn plus 2n plus 1 as n square, because Sn is n square and 2n plus 1 as it is. Then we are going to get the expression n square plus 2n plus 1, which is nothing but n plus 1 whole square, because n plus 1 whole square is n square plus 1 square plus 2n into 1. So, that is n square plus 2n plus 1, which is nothing but n plus 1 square. So, this shows that whatever pattern we had identified for the sum of n odd natural number, where Sn is equal to n square, this holds true for Sn plus 1 term also, that is we are having n plus 1 square. So, we really identified that the sum of n odd natural number, it is true for S1, because the first one was the only summand. So, for only single term it was 1 square. So, that was 1. So, the principle of mathematical induction follows 3 steps. We are supposed to verify the expression, the pattern for the first term, then for the nth term, and then we want to verify for the n plus 1 term. So, by following this pattern, you can legalize the proof. So, what are the steps to perform in the principle of mathematical induction are that let Pn be a statement involving the natural numbers. Then, if P1 is true, the truth of Pk implies the truth of Pk plus 1 for every integer k, and then Pn must be true for all natural numbers n. So, that means we are supposed to verify the statement for the first instance, then for the nth instance, and then for the n plus 1th instance also. So, it is to be noted that just proving Pk plus 1 whenever Pk is true will not work. Let us see how. So, we are having say, but before understanding, we need to that how Pk plus 1 is to be written. We need to understand how to formalize the expressions. Likewise, let us go through a statement that if Pn is a statement where n into n plus 1 is even, then what is P4? Then P4 will be equal to 4 into 4 plus 1, that is 20. Similarly, P10 will be equal to 10 into 10 plus 1, that is 110, because 10 plus 1 is 11, 11 into 10 is 110. So, after going through this illustration, we are able to understand that how to evaluate and how to write a particular term. Now, let me give you one more illustration, that if Pn is a statement where n into n plus 1 into n plus 2 is divisible by 12, then write P3, P4 and P5. You can simply write P3, P4 and P5 by replacing n by 3 in the case of evaluation for P3. Say over here it is 3 into 3 plus 1 into 3 plus 2. So, 4 into 5 is 20 into 3, that is 60, and 60 is divisible by 12. But if we are simply following the pattern in the same manner, say we go for P4, P4 will be equal to 120 and it is again divisible by 12. But the statement wherein we are going to have the value 5, then P5 will be equal to 5 into 5 plus 1 into 5 plus 2. That means the overall result turns out to be 210, which is not divisible by 12. So, this illustration actually helps you to understand that whatever statement say appearing to be true for P3 is appearing to be true for is actually true for P3 and actually true for P4, but it is not true for P5. So we cannot generalize the pattern by looking into a few number of terms. So, so that means each P3 and P4 are true, but P5 is false. So, let's apply the principle of mathematical induction to solve some of the problems. Let me give you an example. That P and B statement where n square is greater than 100, and we are supposed to prove that Pk plus 1 is true whenever Pk is true. So, if we are going for kth term, then because given terms is n square is greater than 100. So, that means k square is to be greater than 100. If you are going to apply for the k plus 1 term, then k plus 1 square should be greater than 100. Expanding k plus 1 square, k plus 1 square is to be expanded k square plus 1 square plus 2k. That means it is k square plus 2k plus 1. Because already we had seen in equation number 1 that k square is greater than 100, then obviously k square plus 2k plus 1 will also be greater than 100, because k square is greater than 100. This implies k plus 1 square is greater than 100. So, that means Pk plus 1 is true whenever Pk is true. So, we had verified that Pk plus 1 is true whenever Pk is true. Now, let us understand the principle of mathematical induction, that by use of principle of mathematical induction we want to prove that 2 plus 4 plus 6 up to 2n is n into n plus 1. We had already learned that 1 plus 3 plus 5 up to 2n minus 1 is equal to n square. So, 2 plus 4 plus 6 is sum of even numbers is 2n is equal to n into n plus 1. Now let us verify it. In order to verify this and apply the principle of mathematical induction, firstly we are supposed to verify that whether the formula holds true for n is equal to 1. Let me get you clarified. In the earlier example, we had not used the term principle of mathematical induction, because for n is equal to 1 square is not greater than 100, because 1 is not greater than 100. This is false. So, that is why principle of over here the question was just to verify that Pk plus 1 is true whenever Pk is true. That means up to certain number it is not true that the statement Pk plus 1, the statement n square is greater than 100 is true for all numbers. It is up to certain numbers it is not true. So, in this case we are expressly using the term use principle of mathematical induction. So, over here we are supposed to verify that whether the statement is true when n is equal to 1 and for the nth term and for the n plus 1 term. So, we denote the statement 1 plus 2 plus 4 2 plus 4 plus 6 up to 2n is equal to n into n plus 1 by the term p n. So, for the first term for n is equal to 1, then P1 will be equal to 1 into 1 plus 1, that is equal to 2, which is clearly true because the first term is 2. Now, we want to verify the step 2 is to verify for any general term, say k. Now, what will be Pk? Then replace by Pk, we mean to say in the expression n into n plus 1, replace n by k. So, the new term will be Pk is equal to k into k plus 1. So, Pk will be equal to k into k plus 1. Now, that means this is true. In order to verify that whether this pattern is true, we need to verify it for the term k plus 1. Now, let us see how we will verify it. So, if we write the expression p k plus 1, then it will be 2 plus 4 plus 6 up to 2k, and the next term will be equal to 2 into k plus 1. Now, that means this overall term will turn out to be k plus 1 into k plus 2. Let us see how. Because if we follow this sequence k 2 plus 4 plus 6 up to 2k, the answer was k into k plus 1, and subsequently we are adding the term 2 into k plus 1, which is the next even number. Taking k plus 1 as common, then we will be having the expression k plus 1 into k plus 2. Taking k plus 1 as common, we will be having k plus 1 into k plus 2. So, this is very true that right hand side of pk plus 1 statement, pk plus 1 is k plus 1 into k plus 2, and we were having pk as k into k plus 1. So, that means, and we were having p1 as 1 into 1 plus 1, that is 2, and that means p1 is true. We assume that pk is true, and we verified that pk plus 1 is also true. It is following the same pattern. So, this shows that the result holds for any value n is equal to k plus 1, and therefore, the truth of pk implies that the value pk plus 1 is also true. So, all the steps are being completed. The first step was to verify the statement for value 1. The second step was to verify the statement for term k and k plus 1. So, we verified by using the principle of mathematical induction that the statement is true for any natural number n. I hope you are able to understand that what is principle of mathematical induction, how to legalize the pattern, and it is observed that many a times the pattern is true for up to some number. Likewise, over here when we proved that k square is greater than 100, we want to prove that k plus 1 is true whenever pk is true, but this statement is not true when n is equal to 1. Also, we learned that up to certain numbers the statement might be true, but after certain steps, certain number, the statement is not true. Likewise, over here in this example, we found that Pn with the statement where n into n plus 1 into n plus 2 is divisible by 12. This statement was found true for 3, P3, P4, but it is not true for P5. So, in order to legalize the pattern, we are supposed to follow the sequence. Likewise, in the first step, we are supposed to verify the statement for n is equal to 1, and in the subsequent step, we are supposed to verify the statement for the general term k, and then we try to verify that the statement is true for the k plus 1 term also. In case all these three situations are true, then the statement is true for any natural number n. Try to apply this concept in solving the numerical problems given into your self-learning material, and you will find that the concept is quite easy and it is a powerful concept to prove various theorems. Thank you very much.